Are CPUs good for AI? Executive summary. Artificial intelligence relies on diverse hardware, and CPUs remain vital despite the prominence of GPUs and accelerators. CPUs excel at orchestration, data preprocessing, inference management, and control flow tasks that GPUs handle inefficiently. Consumer CPUs enable small-scale experimentation, while mid-range workstations support intensive preprocessing and classical machine learning. Server-grade CPUs power large-scale inference, orchestration, and distributed training in data centers, with high-end chips like AMD's 384-thread processors enabling massive parallelism. CPU strengths include versatility, memory capacity, and scalability, but they lag GPUs in throughput, efficiency, and cost-effectiveness for deep learning. Ultimately, CPUs complement accelerators, ensuring balanced, efficient AI infrastructures. Artificial intelligence has become one of the most important drivers of modern computing, influencing everything from personal productivity applications to large-scale cloud services. While graphics processing units, GPUs, and specialized accelerators like TPUs and FPGAs often dominate discussions about AI hardware, central processing units, CPUs, remain a cornerstone of AI workloads. CPUs, whether in consumer PCs or high-end servers, play critical roles in training, inference, data preprocessing, orchestration, and even in some specialized AI applications. The real question is not whether CPUs are good for AI, but rather where they shine, where they fall short, and how their role evolves as hardware ecosystems diversify. The role of CPUs in AI workloads. CPUs are general-purpose processors designed to handle a wide variety of tasks. Unlike GPUs, which are optimized for massive parallelism and floating-point operations, CPUs excel at sequential task execution, branching, and handling complex instructions. AI workloads are highly varied. Some benefit from thousands of parallel threads, e.g., deep learning training, while others involve pre-processing, control flow, or data management, where CPUs are superior. In a typical AI pipeline, CPUs often serve as the orchestrators, data pre-processing, cleaning, augmenting, or transforming data before training, model deployment, managing inference requests, handling user interactions, and integrating AI models into software ecosystems, hybrid workloads. CPUs handle non-matrix-heavy tasks that GPUs are inefficient at executing. Scalability. In multi-node distributed training systems, CPUs coordinate communication and resource scheduling. Thus, while GPUs often get the spotlight, CPUs are indispensable in any realistic AI deployment. Consumer PCs, entry-level AI on CPUs. For everyday users, consumer PCs with CPUs remain the most accessible way to experiment with AI. A modern desktop or laptop CPU can handle smaller AI models, particularly for inference, and frameworks like TensorFlow and PyTorch include CPU backends. For example, running image classification models with modest input sizes, deploying text-based transformers in reduced parameter versions like distilled or quantized models, supporting edge AI applications, such as speech recognition on laptops without dedicated GPUs. However, limitations emerge quickly. Consumer CPUs typically offer fewer cores, 4 to 16 threads on average, and lower memory bandwidth than GPUs. Training large-scale models on a consumer CPU can be prohibitively slow, sometimes hundreds of times slower than using even a mid-range GPU. Still, for experimentation, lightweight applications, or environments without GPU access, consumer CPUs provide a valuable foundation. Mid-range workstations, CPUs with higher core counts. Professional workstations often include CPUs with 32, 64, or more threads. These systems expand the role of CPUs in AI, high-throughput inference in business applications where GPUs are not cost-effective, batch data preprocessing, and feature engineering, where CPU-intensive tasks dominate. Traditional machine learning algorithms, e.g., decision trees, random forests, gradient boosting, which rely less on GPUs and more on CPU-based computations. A workstation with a high thread count CPU can significantly reduce preprocessing bottlenecks in large AI workflows. While they still cannot match GPUs in deep learning training speed, they provide a balanced environment for mixed workloads where AI is only one part of the computational landscape. Server-grade CPUs, scaling AI in data centers. In enterprise and cloud computing, CPUs take on even greater significance. Data centers often deploy server-grade CPUs from Intel Xeon or AMD EPYC lines, designed for reliability, memory scalability, and massive thread counts. These CPUs manage multi-tenant workloads where many AI inference tasks must run in parallel, enable virtualization and container orchestration, critical for serving AI models at scale, drive pre-processing pipelines that feed GPUs with data at the required throughput, provide fallback inference capabilities when GPU resources are unavailable. In distributed AI training, CPUs also handle internode communication, network bandwidth management, and storage access, ensuring GPUs remain fully utilized. Without powerful CPUs, even the fastest GPUs would starve for data or stall due to poor orchestration. The high-end AMD's 384-thread CPU, S. At the top of the spectrum are chips like AMD EPYC processors, offering up to 384 threads. These massive CPUs are engineered for hyperscale data centers and represent the upper bound of what CPUs can contribute to AI workloads. With such enormous parallelism, they are particularly effective at running large-scale inference services that require low-latency response across thousands of concurrent requests, handling data-heavy workloads, such as pre-processing terabytes of text, images, or video for model training, supporting classical AI models that do not map efficiently to GPU hardware, acting as the central orchestrators in GPU-heavy clusters, coordinating workloads across hundreds or thousands of accelerators. Although even a 384-thread CPU cannot compete with GPU clusters in raw deep learning training throughput, it plays a vital supporting role. For example, in large transformer training pipelines, CPUs pre-process and shard datasets, ensuring GPUs can operate at maximum efficiency. Inference at hyperscale, particularly when low latency is essential, may also lean heavily on CPUs due to their efficiency in handling diverse workloads. Strengths of CPUs in AI. 1. Versatility. CPUs can run any AI framework and handle workloads beyond AI, making them the most flexible option. 2. Availability. Every system includes a CPU, so entry into AI experimentation does not require specialized hardware. 3. Memory handling. CPUs often support much larger memory capacities than GPUs, crucial for massive datasets or models that don't fit in GPU VRAM. 4. Control flow efficiency. CPUs excel at nonlinear branching workloads that GPUs struggle with. 5. Scalability in inference. High thread count CPUs, like AMD EPYC chips, enable large-scale inference services. Limitations of CPUs in AI. 1. Throughput for deep learning. GPUs, with their thousands of cores optimized for matrix multiplication, vastly outperform CPUs in training speed. 2. Energy efficiency. CPUs consume more power per AI operation compared to GPUs or TPUs. 3. Hardware ecosystem. Many AI frameworks are optimized for GPUs, leaving CPU implementations slower or less efficient. 4. Cost efficiency. At scale, using CPUs instead of GPUs for training can be more expensive due to higher compute time and energy costs. Complementary roles: CPUs plus accelerators. The most important point is that CPUs and GPUs are not rivals, but complements. A well-architected AI system uses CPUs for orchestration, data handling, and control flow, while GPUs or accelerators handle computationally intensive tasks like matrix multiplications. For example, in training large language models, CPUs feed tokenized data to GPU clusters. In cloud inference, CPUs manage API calls, pre-process inputs, and aggregate outputs before sending them back to users. Even at the highest scale, CPUs remain indispensable, ensuring that accelerators are fully utilized. Conclusion: so, are CPUs good for AI? The answer is nuanced. For small-scale experimentation, consumer CPUs provide an accessible entry point. For professional and enterprise environments, mid-range and server-grade CPUs ensure data pipelines, orchestration, and inference workloads run smoothly. At the cutting edge, AMD's 384-thread CPUs represent the pinnacle of CPU scalability, enabling massive parallel inference and orchestration across AI clusters. While GPUs and specialized accelerators dominate in deep learning training, CPUs remain essential across the AI landscape. They are versatile, ubiquitous, and increasingly powerful. In reality, the most successful AI systems are not CPU versus GPU, but CPU with GPU, where each plays its role in building scalable, efficient, and reliable AI infrastructure.